Hello everyone, welcome to the lecture series on Foundations of Deep Learning, Concepts and Applications. In the previous session, we have seen the derivative of sigmoid, and then we had seen vanishing and exploding gradient problem in a deep neural network. We had seen in general what exactly is vanishing problem and exploding problem. And in today's session, we will see the most important concept of RNN, which is backpropagation through time, which we call it as BTT, and we will connect the challenges such as vanishing and exploding gradients in RNN, and towards the end of this particular session we will see how to fix exploding gradients. So with this let us get started with vanishing backpropagation through time. We will first understand. In our previous session, we had actually seen the we had solved the problem, and when we had solved the problem, we had taken the weights such as Wx, Wh and Wo. These are the weights that we had taken. Now those weights I am changing back to U, V and W. So we have written here Wx, that is input weight, is taken as U, and then the recurrent weight is taken as W, and output weight is taken as V. And why is that we are doing this change? Just to, for a convenient sake, we are doing it. So now what we have to do here is, how are we computing the gradients? How are we updating the weights U, W and V? This is the point of discussion here. So the very first step, let us see how do we update the V. Now here is where there is V. Right. Now, how do you reach to this V, or from V what is the way forward? From V, is it not you have an summation term and you have an activation term here. So which means this summation, let us assume it as a Z, and this is a Y predict, and then we are going to get the loss. So therefore, if you see this particular term from V, we are passing it to summation part, activation part, and then we are going to get the loss. So now since it is an RNN, at every time step we are passing an input. At a time step 1 you are passing x1, at a time step 2 you are passing x2, x3, x4. So at every time step you are going to get this ZT and this Y predicted at a time step T. That is the reason the formula V is, I hope this particular line is clear. So V, from V you are going to get this ZT, and ZT you are going to get YT hat and then the loss. So how can you calculate, how can you write this? Can we write in this way? Derivative of loss with respect to V. Therefore, V new is equal to V old minus derivative of loss with respect to V. This is the formula that we will be writing. So now how can you compute this derivative of loss with respect to V at a particular time step T? Because at every of this time step we have to calculate, right? So at a particular time step T, how can we write this equation? Is it not derivative of loss at this particular time step with respect to this predicted value, and derivative of this with respect to ZT, and derivative of ZT with respect to V. Is it not we write a formula in this way? I hope this is clear. And what exactly is this term? It is at one time step. Then for the overall, for this entire, how is that we will be writing? Derivative of loss with respect to V is a summation over from first time step to all the time steps, is derivative of loss at time t at a particular predicted at that time step predicted value. This is how we will write for the complete model. Now let us compute the values for each of these. So for time being we will first do for one term, then we will do for overall. So first we will understand for the first one. So okay, so how can we write ZT? First let us compute this term. How can you write ZT? What is ZT? If you go back, this is the summation term. So it is H multiply, what is the input which is to this? Is it not HT multiplied with its weight and the bias term? Is it not ZT is written in this way? Now you want to compute this term, and it is a derivative with respect to V. So you do not have V term here, so this becomes 0 and this is HT. Okay, so now let us calculate this term. Now once you get ZT, that is summation, the next is passing it to an activation function. What activation? So YT hat is an activation function for which ZT is passed, Z at a time interval T is passed. If at all, now what this activation function is, suppose if you are solving a regression problem where you are predicting a number, then this activation function will be a linear activation. If it is a linear activation, then YT hat will be just ZT. Correct, whatever, because f of x is x, whatever you pass. Suppose if your aim is to predict, you know, if it is a classification problem, then this function will be sigmoid. If it is sigmoid, then accordingly you will have an derivative of sigmoid f of x 1 minus f of x. So now YT hat is just ZT because f is a linear function. Now what is the derivative of YT with respect to ZT? This term we want to calculate, right? So what will be this value? This is just one number, right? So derivative of a number will be just 1 because it is a constant now. So this is clear. Now let us go back and then calculate this term. Now what is loss? Loss is, because your aim is to predict a number, it is a mean square error. So it is half ground truth at this particular time step minus the predicted value whole square. So when you take the derivative of this, is it not 2 YT minus YT hat, and with respect to YT when you are calculating, is it not this term you will write again and it becomes minus 1. So calculate, is it not minus YT minus YT predict, just a calculation. So expand, is it not minus YT plus YT hat? So can we write this as YT hat minus YT, right? So this term is, so I hope you have understood this. What we have done is with respect to one time step we have calculated. So now overall how is that you will be calculating? Is it not the overall is the summation term? So whatever I have solved by handwritten is been shown here, so that the learners can able to understand what is being written. So at a time step t, for one particular time step, this is the equation, because the path to reach to V, this is the path. So now for an overall for all the time steps you are going to take a summation term. So Z is written in this particular format. This is the formula for ZT, and when you take the derivative with respect to V, we will just get HT. Then this is an linear activation function, therefore the value is 1, and the derivative of loss with respect to YT hat is YT hat minus YT. So for one single time step, this is the formula. Now, for all the time steps, just take the summation of it. This is the derivative of loss with respect to V. I hope this is clear to you. Solve along with me so that you will be able to understand what exactly we are doing it. Now, what is the next step? So far we have seen how do you update V. Now, let us see, this is little tricky one. Let us see how do we update WF. So, now how can we solve this? Let us take, how can we write this term? How can you reach to WF first? So, WF can be reached from loss. You will actually reach to H, and H is an hidden layer neuron, and H is an output of that activation function. So, here you will have an A, which is a summation term. This is summation, this is an activation. So, can we W can be we will be reaching this. First it will go to this summation term, then it will go to H, and from H it will to the loss. Now, so how can you write this term? Can we write it as derivative of loss with respect to WF for one time step? We are writing it for one time step. Later we will see for the overall how do we compute it. So, this will be you can write it as derivative of loss with respect to at a particular time step HT. This is HT, and HT will be in turn to AT. What is AT? At an hidden layer, you have a summation and activation. Summation part is denoted as A and activation part is denoted as H. So, and derivative of AT with respect to WF. So, is it not, this is the path through which you will be reaching to WF. Now, so with this, let us write an equation for each of these terms. First, let us see how do you write for AT. Now, what is AT? AT is this summation term. Now, by now you will be knowing how to calculate the summation term. So, how do for this summation, what are the two inputs that we are getting? The input we are getting from that particular time step, can I write it as xt, right? And then that is getting multiplied with the u input plus input weight, and you are also getting an input from the previous time step. So, previous is H3. So, can I write Ht minus 1? That is getting multiplied with the WF plus the bias term. Is it not? This is the equation for AT. Yes. So, if this is clear to you, how when you take derivative, yeah, this is derivative of AT with respect to WT. Yeah. So, when you take the derivative with respect to WF, so when this term, when you take a derivative with respect to WF, here we do not have this term becomes 0, this term becomes 0 because there is a WF, this is the value, which means this is Ht minus 1. I hope this is clear to you. Next, once you get A, that value is passed to an activation function. So, which means Ht is what activation function we will be using? We are using tan H activation function, and to this what is passed as an input AT. So, what is now you have to take the derivative of it. What is derivative of tan H? The derivative of tan H is 1 minus tan square H of AT. This is derivative of tan H is 1 minus tan square H. So, if this entire term is assigned to Ht, then is it not 1 minus Ht square? This is the answer. If tan H of AT is assigned to Ht, then tan square H of AT becomes Ht square, right. So, which means this term value is 1 minus this. I hope it is clear to you. So far we are clear up till this point. Now what we need to compute is this term. So I am going to erase this and then re-look into it once again. So what we have calculated so far is derivative of loss with respect to WF. I am talking about the overall now will be time t equal to 1 to capital T, derivative of loss with respect to HT, because you are computing this WF. So loss is here from loss to H, and the derivative of HT with respect to AT and derivative of AT with respect to WF. This is what, and we have computed the just some time back that this term value is HT minus 1, and this term value is 1 minus HT square. So I hope up till this it is clear. Now what we need to calculate is this term. So which means we are now calculating derivative of loss with respect to HT. This is the term. This is the term that we are calculating. Now if you look into this derivative of loss with respect to HT, which means at a hidden layer. This is what we are talking about. Now you can ask the question, why is that you are not considering H4? We will understand this. Let us understand that HT is H3. Now when you look into from the diagram, when you look into this H3 is actually going in two directions. One, H3 is going up, and the second, H3 is going right. H3 is going up and H3 is going right. So first let us calculate H3 going up. So is it not when it is going up? So just see from here, when you are going up, what is the flow that what is the flow? Is it not H3 I am writing in general as HT. From HT where will you reach? You will first reach to the summation part, and we know that the summation is denoted as ZT. From summation you will pass the result to an activation, so which is YT hat. From there it is the loss. Okay. So what we are calculating is H3 is going up and H3 is going right. So what we are first calculating is H3 going up. So if H3 is going up, you will write it as derivative of loss with respect to YT hat and derivative of YT hat with respect to ZT and derivative of ZT with respect to HT. This entire you are writing like this. Now let us calculate how do you write ZT. What is ZT? ZT is this summation term. How will you write? What is the input? It is HT. Write an equation for ZT. HT getting multiplied with V, and then the output bias term B naught. So when you take this, when you take a derivative of this with respect to HT, this term becomes 0, and there is a HT here. Therefore, this value is V. Now what is this term? This term is ZT should be passed to an activation function. What activation function we are passing? We are passing and we are using a linear activation function. Then you will get an output YT hat. So when you pass it to a linear activation, is it not ZT only? So is it not this value becomes 1? And this some time back we have calculated all these. So YT hat minus YT. So therefore you see one term value is when H3 going up, you get the value YT hat minus YT multiplied with V. This is what is one term where H is going up at a particular time step T. This is what H going up, Now let us see how do we calculate this part now. H going in the right direction. Let us look into that part. However, in the upcoming slides, you have an answer, properly typed slides are there. So, I am just solving and then showing it to you so that you will be able to understand in a better way. Now, we have seen what is the impact of H3 when it is going in the up direction. Now, we have H3 going right. So, which means H3 is going right here. So, can we write in this way H3, H4 and then to loss, right? H3 to H4 and then you are computing the loss. So, in general, how can you write? Can we write it as HT? 3 is written as a T. Now, 4 is 3 plus 1. So, can we write T plus 1 to and then loss? So, can we write what we are computing, derivative of loss with respect to HT is what we are computing. Sometime back we have seen what is the impact when H3 is going up. Now, what we are computing is H3 going right. So, when H3 is going right, is it not this is the path? This is the path H3 to H4, H4 to loss. So, in general we are writing it as HT to HT plus 1 to loss. So, how can we write this equation now? So, can we write derivative of loss with respect to HT plus 1 and the derivative of HT plus 1 to derivative of HT. Can we write in this way? Answer is yes. Now, we now need to calculate for each of these terms. Let us calculate this. So, what is this term? It is only between H3 and H4. Is it not just H3 and H4? This whole term, is it not HT to HT plus 1? So, what is between HT and HT plus 1? What we have between H3 and H4? Don't we have a summation term, which means we have a term there. So, can we write HT2? Now, we have this term. So, if this is if you are calling this as HT, what is this part? Is it not AT plus 1? So, which means AT plus 1 that is passed to. So, is it not thus? Right. So, how can you write this whole term again? Can we write in this way HT plus 1 to derivative of AT plus 1, derivative of AT plus 1 to derivative of HT? Correct? This is how we are writing. Now, just to go back and then write the equations, substitute the values. So, now you know it very well. How can you write AT plus 1? So, this is what we are writing now. So, to this what is passed as an input? Is it not this is passed as an input? So, xt plus 1, right. If this is AT plus 1 term, this is xt plus 1 multiplied with its weight, and to this the previous input also will come. So, HT multiplied with weight and then the input bias Bx, right. Now, you are taking a derivative of what with respect to HT. With respect to HT, if you are taking, there is no HT term, this becomes 0, this becomes 0, there is HT, that means this is WF, this is WF. Next, what is AT plus 1? AT plus 1 is a summation part, that is then passed to what? Passed to an activation function. So, HT plus 1 is an activation function. Is it not thus? Now, we know what is the derivative of this, it is 1 minus tan H of AT plus 1. If this entire is assigned to H, it is 1 minus H T plus 1 square. So, which means this is 1 minus H T plus 1 square, right. So, what is that we have calculated? We have calculated here. So, in short, what did we do? When you are calculating derivative of loss with respect to HT term, this is having an impact of it is going up and it is going right. So, can I now write overall equation in this way? derivative of loss with respect to ht is actually what? Is it not the combination of two? What are those two combinations? One going up, we are writing it as derivative of loss at a particular current term, loss at a time t to ht, plus going right term. How are we writing a right term? Just some time back we had solved derivative of loss with respect to h t plus 1, derivative of h t plus 1 to derivative of h t. Is it not we are writing in this way? Correct. So, this is exactly backpropagation through time formula. This is important, although it looks very heavy math, but once you start solving along with me, you will be able to do it. So, derivative of loss with respect to ht is, this is a current term, and this is you know, the all the future losses. So, when you are here, imagine in this way, when you are here, one is going right and one is all the future losses. When you are here, it is the current and all the future losses. So, that is what is exactly back propagation through time. This formula what you are seeing here is back propagation through time. So, a quick revision what we have done so far, because since it is an heavy math. So, we have first started with the derivative at a particular time step. We want to find out WF. So, where is how can you reach to this WF? So, just look at the diagram. You can reach this WF from loss L, you can reach to from you will reach to H, from H you will actually reach to summation part, and from summation you will reach to WF. So, that is the formula that you have written here. This is for one time step, this is for summation t equal to 1, this is for the overall. We have first computed this term, we have computed this term. Now, when we take this, so on computing you have got the values. So, you have substituted values back into this formula. When you take this term, this is having an impact where you are one is going up and the second is going right. So, when it is going up, so let me erase so that you will be able to understand. So, when it is going up, so what is the formula? When it is going up, everything you write in general, it is HT. First it reaches to the summation, summation is denoted as Z, ZT at a particular time step, and then you are going to get a predicted value of that time step, and then the loss at that particular current time step. So, substitute the values, you are going to get you know, going up. This is the formula where it is the impact of loss which is going up. Now, second, which is going right. So, how can you calculate which is going right? It is from H3 to H4. So, how can you write H3 to H4 and then to loss? So, can you write H3 as HT, then 4 as T plus 1 and a loss. So, this using a chain rule you are writing in this way. Then between these two terms, you have a summation also. From H3 when you are going to H4, first you have to pass through summation. That summation is AT plus 1. So, again using a chain rule we have written in this way. Take the formulas, write the formulas, do the derivative according to a particular term and see what is the equation that we have got. So, finally, what you have written here is exactly the back propagation through time. So, this is what we have done so far. Let me go back and then continue with our remaining part of the calculation, and then I will show you the slides. So, what we have done so far? We have done a derivative of loss with respect to HT. We know that it is depending on two terms. One is the current term which is going up, and the second is going right. Going right is derivative of H T plus 1 to T plus 1 to H T. Now, what is our ultimate aim? Aim is to find out derivative of loss with respect to W, right. So, since there are so many terms which has come, so let us rewrite this value is yt hat minus yt multiplied with V, and this term we have still not calculated, we are writing it as it is, and we have calculated this term, and this is 1 minus h t plus 1 square into W. What is this? This is derivative of loss with respect to h t. But what is ultimately we are calculating? Is it not derivative of loss with respect to W? Somewhere in your book you would have already solved, you would have written an equation for derivative of loss with respect to W. So, go back, start substituting the values. Is it not for all the terms t equal to from t equal to 1 to capital T, yt hat minus yt multiplied with V plus derivative of loss with respect to h t plus 1 minus h t plus 1 square multiplied with W, and the last two terms. What are those two terms? 1 minus, you will be having in your book, if you have solved along with me, you will be having these equations. So, this is what is overall derivative of loss with respect to W. Now, there is this term, look into this term. This is overall derivative of loss with respect to W. Now, for time being, we are again going back to this equation only. So, I will erase this, and then I am writing the equation again. This is important because now we need to understand what is the gradient descent and exploding gradient descent with respect to RNN. So, what is this? This is a back propagation through time. Now, for simplicity, because there are so many derivative terms, for a simplicity, can we write this term as delta t? Just for a simplicity. Can we write this as GT? If derivative of loss with respect to, this I am writing it as A t plus 1 or capital A t plus 1. So, what did we do? Just a shorter notation. So, can we write now the same equation as derivative of t is equal to GT plus this is derivative of derivative of loss with respect to h t plus 1 A t plus 1, right. Can we write in this way? Now, look at this delta t. So, with this can we write can we write it as delta t plus 1 A t plus 1? Can we write an equation in this form? This is important point, you need to focus here. So, delta t is GT plus delta t plus 1 A t plus 1. What did we do? Because writing too many times that derivative, the formula is becoming big, it is taking too much of space. So, now we have written everything in a short form. Now, let us take one example and then understand here. Now, at a final time step, look at this, at a final time step, you do not have anything further terms, further you do not have anything. So, at a final step, delta t will be GT. This we need to remember. Why? Because we do not have any further terms, that itself is the last term. So, delta t equal to GT. Now, let us take a simple sequence. Let me explain you with 3, t equal to 3. This is important, please focus. So, delta 3 equal to G3, correct. So, when t equal to 3, delta 3 equal to G3, fine. I am doing for t equal to 3, d equal to 2, t equal to 1. So, which means up till here is what we are considering. So, we have not considered t equal to 4, we can even do, but unnecessarily one more step ahead. So, it is t equal to 3, 2 and 1. Suppose our sequence is having a 3, that is what I am trying to explain you. Now, how can you write a derivative delta 2? So, substitute the values in this. Delta 2 is g2 plus this when t equal to 2, this is 2 plus 1 delta 3 a 2 plus 1 is a3, right. Now, substitute the values back, g2 plus delta 3 is g3 a3, good. Now, when t equal to 1, substitute the formula values back into that, g1 plus this is a delta, when t equal to 1, 1 plus 1 is 2 and a t is 1, 1 plus 1 is 2. Delta 2 is this formula, substitute g1 plus g2 g3 a3 a2. So, substitute and then get the values g2 a2 g3 a3 a2. This is your delta 1. So, I hope you have understood up till this. I am pausing here for a second. I want you to go through and then understand what exactly is happening. Okay. So, I am erasing, not erasing, let us have this because it is needed. I have a space here. Now, what is a t plus 1? This is the term which is h t plus 1 to h t. Now, suppose if I want a3, because we have a3, a2, all these are terms, right. If I want a3, can I write it as derivative of h3, derivative of h2? Can we write in this way? And how can you write a2? a2 is derivative of h2 to h1. Can we write in this way? Right? Okay. So, what is that we have done so far? So, no, let me erase so that I will make it clear. What we have got is delta 1 is g1 plus g2 a2 plus g3 a3 a2. This is the equation that we have calculated. So, can we go back and then substitute the values back again in terms of derivative laws, all these can we go back? So, delta 1, what is g? G is derivative of, because it is 1 g1 h1, right, plus g2 is derivative of let me correct it, derivative of loss 2 h2, and what is a2 here? A2 some time back I have written h1 plus what is g3? Derivative of L3 h3, then we are writing it as a3 is h3 h2 and a2 as h2 h1. So, is it not you have a summation term, you have an multiplication term. In general, can we write this as in terms of summation and product, Jacobian term? So, can we write in this way? It looks heavy, right? But this is an important concept. This is the summation is the summation part, and now the this is the product. Product terms, I am talking about the product term. For the first time, this is the first value, right, when k equal to t, when k becomes when k is equal to t, contribution from the current loss. from that current time step. Product can we write in this way, j equal to t plus 1 to k and derivative of h j and h j minus 1, because all are in terms of derivative of loss with h, right. So, substitute back in this, when j value is t plus 1, is it not h t plus 1, and here you substitute derivative of h, j is t plus 1 minus 1. So, is it not we are getting back to h plus h t, is it not you know, back to our 1. So, this is important concept. Why did we explain this? Because now here you have multiple product terms. I am just showing you for three sequence. Now, in general you will be having 50, 100. When you have, can you imagine how many such product terms will come? So, it will be too much, right. So, just imagine if you have one more, you will have it as G4, then here you will have G3 term. So, just imagine you will have so many such product terms. When you have multiple such products, this is where you have your vanishing and exploding problem. You can ask how come vanishing problem, why is it not we have used a tan h here. So, when you take a derivative of a tan h, the value is very small. And where is exploding a problem? In our calculation, somewhere we are getting multiplied it with the weights, right. What if the initial weights are very large? It leads into an exploding problem. So, this term is vanishing and exploding. Now, so this is the reason why RNN suffers with the vanishing problem and exploding problem. So, if you have to understand this big scary formula, here I can write in short as summation k equal to t to capital T contribution of loss Lk to Ht. So, all the future terms. So, this is how you will be writing. When k equal to T, it is an contribution from the current loss. When k equal to T plus 1, the contribution from the next loss. When k equal to T plus 2, the loss after that. So, this is what is you know, the gradient of Ht is the summation of the contributions from all the losses Hk back propagated from time k to time t. So, this is the vanishing and exploding problems, because there are multiple such terms that we have. When we multiply it with the smaller tan h is used, derivative of tan h is a smaller term. When you multiply many such smaller terms, you will have a vanishing problem. And where is exploding a problem? Here we have many such W's and V. If you look, there is a V term which is getting multiplied, and somewhere you will have W getting multiplied. So, in the equation, if you look into this, we have V and W. You are multiplying it with the original values. So, what if the original weights are very large? It leads into exploding a problem. So, this is again you know, what we have discussed. You know, you can able to see all those calculations here. So, the final derivative of loss with respect to W is written in this way: delta t 1 minus Ht square into Ht minus 1, where delta t term is this. Although it looks heavy, but start solving step by step, you will be able to understand. Now, we have come to an last weight update, which is U. Now, we need to update u. This is a very simple easy way. How can you reach to u? What is the step, what is the path that you will be able to get this u? Is it not this is the path? So, first u reaches to this summation, then activation, here you have summation, then activation. So, is it not you will have the following path? So, how can you write this? I hope you have understood this. From I am showing you the forward, so that when you are back propagating, you will be able to easily write the chain rule. So, you have a summation term, and that summation term is written as a, and since you are doing at a particular time step, it is a t, and this is h t. Here you have z t, then you have y t hat, and then you will have a loss function. So, how will you write the chain rule? Derivative of loss at a particular time is y t hat, then y t hat with respect to z t, then we have z t with respect to h t, then we have h t with respect to a t, then we have a t with respect to u. This is at a particular time step, which means derivative of loss with respect to u at a particular time step. So, now go back and then start substituting the values. By now most of the terms we have already calculated. This is loss, so y t minus predicted value minus ground truth, and this is 1. And what exactly is derivative of, in case if you are not able to, just substitute the values a t. How will you get to this a t? It is current term multiplied with u, and for this the previous h t minus 1 getting multiplied with w, and then the input. So, when you take derivative with respect to u, this term is x t. And next, what is this term? It is passing it to an activation. H t is tan h of a t. So, which is 1 minus h t square. So, this is 1 minus h t square. Then what is z t? How will you write z t? Z t is h t getting multiplied with v plus output bias. So, when you take derivative with respect to h t, it is v. So, this is v term. Derivative of loss with respect to u at a particular time step is this formula, but it is not at a particular time step, right? You have u in all of the previous one. So, therefore, derivative of loss with respect to u is a summation t is equal to 1 to capital T. Now, how will you reach to u? So, here derivative of loss with respect to h t with respect to a t with respect to u. Now, what is this one? Just some time back we have calculated, this is nothing but delta. Can we take it as delta t, and what is this? We have calculated 1 minus h t square, and what is this? This is x t. Now, you should be able to recall what is delta t, the big formula what we have seen. So, it is y t hat minus y t getting multiplied it with v plus delta, again you have one more term 1 minus h t plus 1 square w. So, although it looks heavy, but again neatly it is been written in the upcoming slide. So, whatever we have seen by handwritten, you can able to see this here. So, this is what is back propagation through time, where you are updating the weights v, w and u, and we have also understood how we are having a vanishing problem and exploding a problem. With this, let us see the last topic, how do you fix the exploding gradients. So, what are the different methods that are used for fixing the exploding, because vanishing problem is happening because of the activation function that is used at the hidden layer. if the hidden layer uses a ReLU activation function, then you can able to control the vanishing problem. But what are the different techniques to solve the exploding gradients? Why? Because exploding is all happening because of what if the initial weights assumed by the model is large. So how will you solve it? So let us see, there are some techniques. The first technique here is gradient clipping. So you can able to see from the slide, the first method is gradient clipping. Now how will you solve this gradient clipping? Most importantly, we will be using this because RNN suffers heavily with the exploding gradients, because there are two weights that are getting multiplied V and WF. So how will you solve a problem here? So the first technique, most important, is gradient clipping. So how exactly gradient clipping works? We will see this with an example only. So first let us assume you have an input data. For that input data, you will have an weights, you will have an X and Y, that is the data, input data, and then the target value Y. Then you are going to build an model. When you are building a model, you will have an weights and then the bias. This is an initial and these weights are randomly initialized. So let us assume these weights are small weights only, okay. And then forward, you will compute, you will start the process, you will do a forward pass. In the forward pass, what is that we get? We get a predicted value and we compute the loss. So how will you get Z? Z is weight multiplied with input plus bias, and this Z you are passing it to some activation function and you get a predicted value. Ultimately, once you get a predicted value, you compute the loss. How will you compute the loss? Loss is always computed between ground truth and predicted value. If the ground truth is Y and the predicted value is Y hat, you will compute the loss between these two. Now, based on what kind of a problem that you are solving, accordingly you are using that activation function, and what kind of problem you are solving, accordingly you will be having a loss function, function also. So here let us assume what are the weights here. Let the weights be W1, W2 and bias. Now, during a back propagation, what is that you will do? You will compute the gradient of loss with respect to W1, gradient of loss with respect to W2, and then the bias. Now, how exactly gradient clipping works? Let us assume let the gradient with respect to W1 value is 12. Gradient of with respect to W2 value is 16, and bias the value is 9. Let us assume this. The very first step is calculate the square, this is the first step that you should do. Okay. So when you compute this, you will get approximately 21.93. Okay. This is the first step. What is the second step? Fix one threshold. So what is a threshold? Let us assume the threshold value what we have fixed is 5. When the gradients are increasing, you have to limit the gradient. Now, so this value is very much greater than 5. Therefore, third step is calculate the scaling factor. How will you calculate the scaling factor? 5 divided by 21.93, which will be approximately 2 to 8. Fourth step, what you will do? Multiply 0.228 with each of these gradient values, 12. Then multiply 0.228 with the 16, multiply 228 with the 9. So what did we do? We have computed the gradients. In the back propagation, we computed gradients. Let us assume the gradient values are each of these. First step is you have computed the gradient norm. You have computed the gradient norm. The gradient norm value what you have got is this. Then you have chosen the clipping ratio, clipping threshold, not ratio, I am sorry, clipping threshold. Let the threshold be 5. Then since this gradient norm is greater than the clipping factor, next you are calculating a scaling factor. So, you have got this, then you are multiplying each of these gradients with this value. This is what we have done. We have done this so far. Now, let us assume the initial weights learning rate is 0.1 and the initial weights W1, W2 and the bias term is 1 minus 2 and 0.5. Let us assume these values. W1 value is 1, W2 value is minus 2.0 and B value is 0.5. How will you update the weights? Is it not W new is equal to W old minus learning rate and derivative of loss with respect to weight? So far if ideally you were writing it as derivative of loss with respect to W1, derivative of loss with respect to W2, derivative of loss with respect to bias. But because it is gradient clipping, it is no more this value directly, it is the clipped value. How did you get this clipped value? Go back. You see this 0.228 is getting multiplied with 2. 0.228 is getting multiplied with this and it is multiplied with 9. So, these are the values that we have got. So, in a normal way we used to multiply it with those gradient values. Ideally we were supposed to multiply it with 12, 16 and 9, but here we have used the clipped value, gradient which is clipped. So, those values have been used. So, because of this you can avoid, this is the most popular method called gradient clipping. So, how do the gradient clipping works? This is the steps that are used, and what gradient clipping is doing, it limits the magnitude of gradients before going for weight updates. This is what is one method. What is the second method? It is all dealing with the weights, right? So, rather than allowing the model to randomly initialize the weights, so use certain techniques to initialize the weights. Do not allow the model to choose the weights randomly. So, suppose if you are building a deep neural network where there is a ReLU activation function that it is used at a hidden layer, then weight initialization should be using he method. If you are building a neural network where tan H or sigmoid activation function is used at a hidden layer, then use an Xavier method for initializing the weights. Or if you are using an RNN methods, then go for an orthogonal initialization of weights. So, use a proper weight initialization method. The next technique is you can use an appropriate activation function which is ReLU or the variants of ReLU. However, this is not applicable to RNN, because at RNN we will be using tan H. I am talking about in general how do you avoid a gradient, not very specifically with respect to RNN. Then fourth technique, you can use regularization and optimizers. L2 regularization you can use, that will control the exploding gradient, or you can also use an optimizers such as RMS propagation and ADAM. You can use these kind of an optimizers, it will control the exploding gradient. You can try adding a dropout batch normalization, that will also control. Then whenever you are using RMS propagation, ADAM or any of those advanced optimizers, rather than calling direct function, rather than calling default one, call a function so that you can control the learning rate. So, smaller the learning rate, then this whole term becomes very small. When the whole term, when this value is very small, when you multiply that with this entire term is small. When this term is small, once again the convergence will be very slow. New weight will be old weight. So, do not fix a very small learning rate also. At the same time, do not have a very large learning weight. When you have a very large learning weight, then it overshoots the minimum and then causes an exploding gradient. A loss will oscillate too much. So, we have to go for we have to adjust the learning rate during training. These are some of the techniques that are used for avoiding the exploding gradient problem. So, this is not very specifically with respect to RNN, what we are discussing is in general. And more specifically to RNN, we can go for gradient clipping method. So, with this we have come to an end of the particular session, and this is an end of our sequence to sequence model, which is our week 7, and in the next session of this particular week, or the last session of this particular week, we will see the hands on implementation, where we will see the different variants of RNN also. Rather than just a simple RNN, we will see some of the variants of RNN. Thank you.